Hi, y'all. We're back at the workbook, lesson 8. We are doing graphing log functions today, and we're going to be looking at some different transformations of the log function. We have already talked about how the basic log graph is the inverse graph of the exponential graph, which looks like this, and the log graph, therefore, the inverse, would be a reflection over the line y equals x, and it looks like this one here. Okay, so we're going to look at some transformations of that graph. All right, in particular, we're looking at how the base, if we change the base from an integer, or sorry, a whole number to the reciprocal of that whole number, how the graph is affected. And that's on part 1 here. One thing to note, anytime a log function passes through x equals 1, if you think about that, let's look at our log function, log base b, and let's say x was 1. Okay, so we're talking about this point here. Well, we know that anything can be expressed as something to the 0 exponent, and you would get 1. So, for instance, we could have log base b, and let's make it b to the 0, and that would still equal 1. So in other words, when x is equal to 1, okay, the value of y is going to be equal to, why did I write 1 here? Sorry. The value of y is going to be equal to 0. The exponent is 0. So this point on any graph in this form is 1, 0. The x-intercept is 1. All right, so the graph of y equals log base 3 of x, okay, passes through the point 3, 1. Why? Because we would have log base 3 of 3, okay, and therefore what would the y value be? Well, that whole thing would equal the exponent, which is 1. Okay, so let's look at these graphs. Each of the following complete the statement and sketch the graph on the grid. Use the graphing calculator. We could use the graphing calculator, or we could just use this basic graph and go from there. Let's take a look at the first one here. Y equals log base 10 of x passes through the point. Now let's think, if we want y to be 1, what would we have to make x equal in this equation? So what would go here? Well, remember what the log is the exponent. So if the base on this is 10, if we wrote 10 to the exponent of 1, there we go. That's how we would get that. Okay, so that would have to be a 10. So to graph that, we would want to make sure we're going to go through this point for sure, because we know that's the same for all of these. And then when x is 10, y is 1. So we are right there. The graph should look something like this. Okay, and that would be y equals log base 10 of x. Okay, what if it was log base 1/3 of x? So what value would x have to be such that the value of the log was 1? Well, it would be 1/3, because log base 1/3 of 1/3 would equal 1. So that graph, let's do this in a different color. At x equals 1/3, so say somewhere in there, y would equal 1. Oh, that's interesting. I'm trying to think, if x was, say, 1, that would have to be, let's see, let's pick something a little nicer, like 3. I could write 3 as 3 to the negative 1. Oh, interesting. So if x was 3, we would have a value of negative 1. Okay. How would we graph this on the calculator? Let's think about that, because we haven't really talked about that. But what you could do is use your change of base formula and write that as log x divided by log 1/3. Let's maybe try that out. Bring up the graphing calculator. Okay, so in the calculator under y equals, we've put log x divided by log 1/3, and that's how we're going to graph log of x, log base 1/3 of x. Okay, we'll go zoom standard just in case we have to check this, change it back to normal. Oh, look at that. Let's change our windows so we're going from 0 for x, and that actually should be fine. Okay, so that's interesting. The log function now is basically coming down like this, as opposed to before where it goes up and crosses and goes like that. So basically what's going on here is we have a graph that looks like this. And let's see if we can get another point. When x is 9, let's see here, if we had log base 1/3 of 9, if I could write 9 as 1/3 to some exponent, I guess what I would do is write it as a 3 to the 2, and then reciprocal that 3 to get 1/3. So it'd be 1/3 now to the negative 2. So at x equals 9, we would be down at negative 2. There we go. That is our y equals log base 1/3 of x. Notice how it compares to the original graph here, y equals log base 3 of x. Yeah, it does look like it's reflected over the line or over the x-axis. Look at that, this point to this point. Okay, so what do you think this next one would be? Probably a reflection of this blue graph we drew, right? Let's see, what value would we need for x such that this would equal 1? Well, that would probably have to be a 1/10 again. Okay, so when x is 1/10, good grief, how are we going to graph that? 1/10. Okay, so it's really close in there. Okay, now let's think of something else that we could plot, like base 1/10 and then maybe a 10. Okay, so we'd have to write that 10 as 1/10, so that would have to be 10 to the negative, 1/10 to the negative 1. So when x is 10, y would be negative 1. And we still go through at x-intercept at 1. So it looks like our graph for that one would look something like this. There we go. Okay, good. So in essence, what have we discovered? We're not going to graph those two. Okay, what have we discovered? Let's fill in our domain and range table. So domain, well, for all of these graphs, you probably discovered that x was greater than 0, right, for each one of those. Or if we wrote that in interval notation, that could also be written as 0, infinity, meaning greater than 0, basically, from 0 to infinity. And that goes for all of these. I'm just going to put little tick marks. Okay, the range, you'll notice it goes forever up and down for all of those graphs. So our range is going to be y's and elm in the reals. Or if you wanted to write that in interval notation, negative infinity to infinity. And then the range for all of those are all the same as well. So I'll put little tick marks there. Okay, x-intercept, as you notice when we were talking, the x-intercept for every one of those graphs was 1. Okay, that's easy enough to write all the way down. And the y-intercept, oh, did you guys notice? It didn't cross the y-axis, did it? So for y-intercept, we would say none. And that seems to be the same for all as well. Okay, asymptote. Well, it didn't cross the y-axis, did it? It seemed to, every time one of those graphs approached the y-axis, but it didn't quite cross it. So that means our asymptote, our vertical asymptote in particular, is the y-axis. How do we describe that with an equation? Well, everywhere on that y-axis, x would equal 0. So that would be our asymptote. X value when y was 1. Now this changes depending on which graph it was. So when y was 1 for the original, y equals log base 3 of x. When y is 1, go to 1 here, go across. Oh, and it was that value, which was 3. Okay, which kind of makes sense, right? How else would we get an exponent of 1? It would have to be, the x value would have to be the same as the base on the log. So all of these, as a result, would be whatever the base was. 10, 1/3, 1/10, and therefore the same thing for log base b of x. That will be, you got it, b. Good, let's look at the next page. So how do the graphs of log base 3 of x and log base 1/3 of x compare with each other? Well, as we discovered, they are reflections of each other in the x-axis. Okay, same thing for the next question, ditto. Okay, and then complete the following statement. The graph of y equals log base 1/3 of x is a reflection in the x-axis of the graph of y equals log base b of x. Okay, good to know. In the transformation unit, replacement for reflection in the x-axis is that y goes to negative y. So let's start with y equals log base b of x and show why that is algebraically. Okay, so log base b of x, and we're going to replace y with negative y. There we go. Okay, now let's do some manipulating here to see if we can get this looking like the other equation. Okay, so now what we're going to have to do with this equation is we're going to have to somehow get base of 1 over b to show that this above statement is true. So first thing we're going to do is we are going to basically eliminate the log on the right-hand side. And to do that, we're going to raise both sides into the exponent. Okay, there we go. And then we would have b to the negative y equals x. Okay, now we're going to log both sides again, but this time we're choosing base 1 over b instead, so that it can look like what we're trying to show is true. Okay, so we logged both sides, we chose base 1 over b. Now, we could manipulate this a little bit. Notice we have b to the negative y. Well, I know that b to the negative 1 is basically 1 over b, right? So let's first write it like that. Okay, and then I could write that as 1 over b, like that. And what I've just discovered then is now my base on my log and my base on my power inside the log are the same. So therefore that whole left-hand side should just equal the exponent, which is y. So we have y equals the right-hand side log base 1/3 of x. And there we go. We've proved that by doing a reflection in the x-axis, we basically get the equation y equals log base 1 over b of x. All right, so we've kind of done the math already to prove this result, so we're going to move on to not part 2, we're going to actually skip to the part after that. So we're on this page now. Part 2 won't be on your test or your diploma, so we're going to focus on this, further transformations of log functions. So using all our transformations, we're going to look at basically what it does to the graph of the log function. So we have the graph of log base 3 of x shown here. Write the transformation associated with each of the following and sketch the graph on the grid. So we're going to do this. Okay, so think transformations. I have, if we're comparing it to the original, y equals log base 3 of x, I basically have a 2 in front of my whole function. Well, if you recall, that means that we have a vertical stretch by a factor of, abbreviating a few things here, by a factor of 2 about the x-axis. All right, so we've got kind of what the transformation would be. Now let's sketch the graph for that one. So let's take some kind of anchor points here, I guess. And maybe this one here. Where else does it go through? In here. And we're going to vertically stretch by a factor of 2. So this point won't go anywhere because we're stretching about the x-axis and it's on the x-axis. This one here, let's do this in a different color, will be stretched. It's a different distance of 1 away from the x-axis, so now it would be a distance of 2 away. So right here, that one's still there. This one is a distance of 1 above the x-axis, so that would be now 1 times 2, so it goes to here. And then this one finally has a y value of 2, so 2 times 2 puts us at a y value of 4 right there. Okay, so let's draw that graph now. Okay, so that should look something like that, and let's label that y equals 2 log base 3 of x. Okay, you guys try the next two. We're going to have some translations involved and all sorts of things. So see if you can try the next two and we'll go over those, okay? Pause your video, please. Okay, so you tried the next one and we replaced x with x minus 2, so that means the graph moved right 2. So if you take these blue dots on the original graph and move them to the right 2, okay, you should get a graph like this, but did you draw it going kind of like that? If you did that wrong, because here's what you have to do. We know we have a vertical asymptote right on the y-axis, right? So if we move the whole graph to the right too, we need to move that asymptote as well to the right too. So we want to be making kind of a dashed line going on basically x equals 2. And then when we draw our graph, we don't cross that line. Okay, so we just go like that. There we go. That would be the graph of y equals log base 3 of x minus 2. Now the next one we're going to do as well, but please note that x minus 2 now is not inside the brackets. It's just assumed to be whatever immediately follows x. So you guys go ahead and do that one. We'll finish it up in part 2 of this video, and I will see you then. Okay.